This circuit contains an operational amplifier with a couple of feedback loops, one in the negative side and one in the positive side. And also it contains a capacitor here. And what we're being asked to compute is the relationship between the output voltage and the input voltage. Pretty much, let's figure out what this particular configuration does. All right, so we'll get started in here. Well, our assumptions are as usual. Vn equals Vp. Basically, the inverting and non-inverting voltages are equivalent for an ideal case. And of course, I of n is 0 and I of p is also 0. So there's no current in here. That will be the I of n in here. Okay, and there's no current in here. That will be the Ip is 0. All right, so do we know the V of n readily? We don't. Okay, do we know the V of p? Well, we don't. It's not obvious. It's not connected directly to Vi or 0, so we need to write maybe a couple of equations, one in here and one in here. Of course, we're trying to avoid writing any equations in here because we don't know the current leaving here. All right, but I'm looking at this in here. Well, these two resistors, which is R and R, well, technically, whatever current, let's assume that there's a current leaving from here, it comes in here, it comes in here. So they share the same current, so they're technically in series. And because they're exactly the same value, this is R and this is R, so this voltage in here is simply half of the input voltage. And the input voltage, well, half of the source voltage, not the input voltage, because this is the input voltage. So the source voltage for us in this particular case is V output. All right, so of course, if you're more comfortable, we can write a nodal equation if you're more comfortable with that. But I can tell you that V of n is just simply basically 1/2 of the output of t. That's pretty much what it is. If you write nodal equation, which I can show you, let me just write that nodal equation so I can show you. V of n minus 0 divided by R plus V of n minus V output divided also by R equals 0. And you do the calculation in here, and you'll end up with basically V of n plus V of n minus V output equals 0. That means 2 V of n equals V output equals V output. That means V of n is just simply half of V output. That's basically the same thing we figured out directly from just voltage division. Okay, so I'll remove these in here so that it's a little bit cleaner. Okay, and then we come back in here. So we know actually Vn and Vp, because Vp is also half of V output t. So what I do now know is the voltage in here. So now, do I need to write an equation? Well, it won't hurt us to write the equation even though we know this voltage in here, so because we know how much exactly it is. So let's write an equation for this guy, and this guy in here. That's what we will do. All right, so the nodal equation at the second point will be, well, I'm going to call it Vp minus Vi, and all of them are functions of t, so I can just basically do that, divided by R, plus I'll call this here Ic, and this basically is plus minus. Okay, so I of c, which is actually, yeah, well, let's leave it at I of c for now. And then Vp of t minus V output of also t divided by the same R. This is basically the current leaving in here. So I wrote one current in here, one current in here, one current in here. And of course, we ignore the current in the last one because nothing goes into the ideal operational amplifiers. We say this is 0. Then we have to substitute the value of I of c. We know that Ic is just simply c times dV divided by dt. But what's the V? Well, let's take a look in here. If I assume that the voltage across this capacitor is from here to here, it's pretty much simply, it's Vp. This is here, is between here and here, is just simply Vp. And we know what Vp is, so let me just substitute it. So that will be C, and of course, passive sign convention, I didn't look at it. The current is leaving in here. It's actually hitting the positive first, so it's positive. So this is correct. So that will be C times D. What's the voltage? Well, it's the Vp of t divided by d of t. That will be the Ic of t. All right, which is basically C times, and I can substitute it in here if I wanted to, but I know what it is in terms of V out. Well, why don't I just do this here and then substitute what the P output is? All right, so what I'm going to do is I'll just take this one here and just put it in the IC. So will tell me it's Vp, which is a function of t, minus Vi, which is also a function of t divided by R, plus C times dVpt divided by d of t, plus Vp of t minus V output of t divided by R. All right, what we really need to do is we need to isolate these V output on one side, but of course before we do this, we need to substitute the V of t because the V output will assume will contain it. So that will be basically half of V output t, okay, minus V input t divided by R plus C times, I believe that will be C divided by 2, d V output T divided by d of T, plus, I believe that will be V output, which is half of V output T minus V output T divided by R. And that equals 0. This equals 0, by the way. Alright, so now let's do this here. A little bit of algebra. That will give me 1 divided by 2R V output of T minus 1 divided by R V input of T plus C divided by 2 dV output of T divided by d of T plus 1 divided by half V output of T. Actually, we can combine these two here together. That's simply half minus 1 is just simply negative half. Okay, so that will be negative 1 divided by 2R V output of T, and that should be 0. So if we multiply by R, or actually maybe we can multiply by 2R, we'll get V output of T minus 2 V in of T plus, because we multiply by 2R, we'll get RC dV output T divided by dt, and minus, because we multiply by 2R, V output of T equals 0. Alright, do we actually have anything that we can clean? I believe this V output of T and this V output of T will go away. So that leaves us with, I believe, 2, well, let's do it that way. We'll get dV output of T divided by d of T equals 1 divided by RC, and I believe that will be 2 VI of T. Okay, so what I've done is I moved this to the other side, okay, and that became 2VI. This is the 2VI in here. And I took this one RC and I just divided both sides. Alright, so what we're interested in is V output in terms of V input. So what we have to do is we have to say dV output of T equals 2 divided by RC times VI, which is a function of T times d of T. I'm interested in the T, so what I will do, or V output of T, I'll take the integral of both of these sides. So that will tell me V output of tau, actually dV output of tau from T0 all the way to T. And if we assume that the T0 for now is just simply 0, okay, we can just assume that this is 0 all the way to T, equals 2 divided by RC, and this is from 0 to T, V input of tau, d of tau. Okay, so we do this here, we will end up with V output of T is just minus V output of 0 equals 2 divided by RC from the integral from 0 to T, VI of tau, d of tau. And if we, for sake of simplicity, we assumed that initial voltage output is 0, we can just simply remove this in here if we assumed it. Alright, and what we end up with is this particular equation. So if I actually copy this equation and just put it next to the output in here, just to see how does the equation relate. So what you will see that simply here. Okay, let me just do this here. So I went ahead and did it. Okay, so what you simply see that the output is simply the integral of the input. That's what it is, with some sort of a scalar. And this particular scalar has positive in here, not negative. So as it turns out to be, that this here is a non-inverting integrator. That's what this particular circuit configuration does.